Welcome back, guys. In today's video, I'm going to be covering resonance. Now, the best way to go over resonance, in my opinion, is with an example. So let's take a look at this molecule over here on the left to help us understand resonance a little bit better. So we have this carbon right here. It's bonded to 3 hydrogens. It's also bonded to this carbon in the center here. And we could take a look at these oxygens and see that one of them has a double bond and 2 lone pairs, no charge, and one of them has a single bond, 3 lone pairs, and a negative formal charge. So when are we going to see resonance come into play? So when I think about resonance, I think about drawing Lewis structures where I made an arbitrary decision on where I placed some of my double bonds and lone pairs. Now, if you've never worked with resonance before, that might sound a little bit confusing. So let's make sure we walk through this, pretty slowly. So let's go back to our Lewis structure. Now, when I was drawing out this Lewis structure before I started the video, I made an arbitrary decision to put the double bonded oxygen here and the single bonded oxygen here. What do I mean by that? Let's say, instead of drawing it this way, I decided to flip this around. So I drew, the double bond here on this oxygen, the single bond here. I put 3 lone pairs on this oxygen, and the negative charge here. Okay, so when we think about resonance, we need to be on the lookout for Lewis structures where we make decisions on where we place double bonds and lone pairs where it didn't matter where we put those particular bonds, right? Now, on the contrary, if we look at the left side of this molecule, right, it definitely mattered where we put these bonds, right? These single bonds right here, we definitely don't want to start moving them around, right? If we get rid of this bond, this hydrogen is going to go floating away. If we get rid of this bond right here and start moving it around, the left side of this molecule could become completely detached from this, whole Lewis structure. So when we're working with resonance, we want to be working with delocalized electrons, right? So delocalized electrons are going to be electrons that are not associated with a single atom or covalent bond. So that's what I was getting at over here, right? These electrons would be considered localized electrons, right? They're in one place. They're associated with one atom, right? We don't want to move them around. So a good trick or a rule of thumb when you're thinking about delocalized electrons, you're going to be thinking about double bonds and lone pairs. Okay? So when you see single bonds, you're really not thinking too much about resonance, right? When you see double bonds and lone pairs, in the same area of a Lewis structure, you want to start thinking about resonance, right? So this structure and that original Lewis structure I have with these oxygens flipped are equally contributing Lewis structures, right? And when you have equally contributing Lewis structures, right, there's no difference between them other than the bonds and where you put them. Those are called resonance structures, right? So you'll often see questions asked like, how many resonance structures does a certain molecule have, right? So we want to look for double bonds and lone pairs. We want to look for electrons that we can spread out, right? So delocalized means they don't have a home, right? They don't have one singular place or bond that they belong to. You could actually spread them out between different atoms in the molecule. So with that being said, let's take a look at CO3 2- and see how many resonance structures we can draw. So let's erase this. Okay, and this is actually a tricky Lewis structure to draw, so I'm actually going to go slow when I walk through this Lewis structure. It will actually help us determine the resonance for this molecule. So we have CO3, okay? How many valence electrons do we have in this molecule, right? So if we have CO3 2-, right, this is going to have 4 valence electrons, right? This is going to have 6, 6, and 6, right? So 6, 12, 18, 18 plus 4 is 22, and it also has a 2- charge. So 22 plus 2 is 24 valence electrons, okay? So we have 24 valence electrons to work with. Again, I'm just drawing the Lewis structure nice and slow so we can walk through this. Then I know that carbon needs to make 4 bonds so that it can complete its octet. So I'm just going to arbitrarily pick this oxygen over here to draw this double bond. Now I should already be thinking in my head, I have 3 oxygens. Why did I pick this oxygen to have the double bond? Couldn't I have drawn the double bond somewhere else? Well, we're going to see that resonance is going to come into play here. So let's see how many electrons we have left to work with, right? We've used 2, 4, 6, 8. So we have 16 left, right? So this oxygen, to complete its octet, right? So it has 8 total electrons. We can give it 2 lone pairs. We know the rest of them, or these other 2 oxygens, I should say. Let's give them 3 lone pairs each, right? And that should successfully create our CO3 2- Lewis structure. Okay? Now, let's take a look at this molecule. Like I said, when I was drawing this out, why did I pick this oxygen to make the double bond between the carbon and the oxygen? Right? I actually randomly picked that. I very well could have drawn it this way. Could have drawn this one here, this like this, right? Now this has no charge. This has a charge of -1, right? Now we're back to the same Lewis structure. However, the double bond is here and the single bond is here, right? These are delocalized electrons, meaning they don't belong, I should say, to a single atom or bond, right? Double bonds and lone pairs, we can see, right, with these delocalized electrons, they're electrons that are moving around the molecule, okay? And again, right, we had our first structure. This is our second structure, right? Now we can even go as far to make a third resonance structure, right? A third Lewis structure that is equal to the other 2. What happens if instead we put the double bond here? Now, let's keep this lone pair here, right? So now we've seen the double bond be here, here, and here, right? So what we can see is that there are 3 equally contributing Lewis structures, or 3 equal resonance structures for this CO3 2- molecule. So just remember, resonance, you want to be on the lookout for it when you have delocalized electrons. You have these double bonds and lone pairs that can be moved around, right? And anytime you find yourself making an arbitrary decision where you're putting lone pairs or double bonds, you want to be on the lookout for resonance. So make sure to give this video a thumbs up and check out more videos on the channel.